We're now continuing our lesson that is discussing alkenes, double-bonded hydrocarbons, and alkynes, triple-bonded hydrocarbons, both that are unsaturated. We're being asked to describe physical properties of these alkenes and alkynes. We realize that both of those compounds are considered nonpolar and that the only attractive force between their molecules are those weak London dispersion forces. That their physical properties, therefore, are very similar to alkanes in the way they behave with their skeletal carbons. Alkenes and alkynes that are liquids at room temperatures tend to have densities less than that of water, 1 gram over 1 mil. So if they're less dense than water, they indeed will float on the surface of water. And since they are indeed nonpolar, they will not dissolve in water. Simply recalling earlier that likes dissolve likes. So if water indeed is a polar molecule and a hydrocarbon that contains either double or triple bonds is a nonpolar substance, the two would not mix well together. We will also discuss a chemical family of very important molecules known as terpenes. These compounds are often found in essential oils of plants, and substances known as terpenes have something in common in terms of their carbon skeleton. They can always be divided into at least 2, but usually more, carbon units that are identified with a 5-carbon skeleton called isoprene. Isoprene is this structure right here. It's a 5-carbon unit. 1, 2, 3, 4, 5. Now you can see how they got the term iso because this tail here is branched. A 5-carbon unit that contains a diene. Now notice what they've done when we number the carbon, of course, starting here to give the substituent group the lowest possible number. 2-methyl. On the second carbon, we see 2-methyl. And between carbon 1 and 2, and between carbon 3 and 4, we have the diene. So the IUPAC name for this carbon, a common name called isoprene, is indeed 2-methyl 1,3-butadiene. The carbon that is closest to the substituent group, known as carbon 1, is given the name head of the molecule. The terminal carbon, which is the end of the 4th branch, is called the tail of this carbon chain. What we begin to see is that these monomers come together head to tail to build quite large polymers that give us very large molecular structures found in living systems. We understand when we're building large molecules, the simple subunits that are bonded together are always controlled by enzyme-catalyzed reactions. That enzymes usually will increase the rate of reaction, although sometimes it can be used to decrease the rate of reaction. If we choose to modify one of our long carbon chains, it would also involve an enzyme-catalyzed reaction. Enzymes are the control factor, where the molecule reacts with another and how fast the molecule reacts with another. So terpenes really are very widely distributed in the biological world, and studying their structure provides a glimpse into the wondrous diversity of nature, just generated from a simple monomer, where head-to-tail structures have been created. Here are some examples of terpenes that we find in nature. Myrcene, bay oil. Geraniol, EIOL, we see in roses and other flowers, giving us the scent often found in even just marketed perfumes. Lemon and oranges has a terpene format. Menthol, as in peppermint. Farnesol, that's found in lily of the valley. And even vitamin A, sometimes marketed as retinol, especially in face creams, you'll hear retinol. But you can see where the site of attachment from one isoprene connects to a second isoprene is always from a head to tail. And you can see that they've color-coded those in red. And if an additional ring forms, making the entire structure cyclic, they're showing that structure as in green. So again, just a nice basic unit, a small unit in nature, but what becomes powerful is the way those arrange themselves give us quite remarkable molecules. We next discuss those characteristic reactions of alkenes. The most characteristic reaction of alkenes is addition to the carbon-carbon double bond. We break that double bond and in its place form single bonds, and new atoms are attached to those carbons. We go from an unsaturated hydrocarbon to a saturated hydrocarbon, where each of the carbons now contains 4 sites of bonding. A first example, hydrochlorination. Hydrochlorination. And again, we'll talk very specifically about the mechanisms in which these reactions occur, but a quick snapshot, taking the double bond and breaking it to a single bond, giving a site of attachment for an H and Cl. HCl. One hydrogen to this carbon, the other chlorine to this carbon, or vice versa. Hydration, splitting the carbon bond and adding water. I like to think of water as HOH. Bromination, really it could be any halogen, so perhaps a better word here would be halogenation. Thinking about the halogens, it could have been fluorine, chlorine, bromine, or iodine. If it's being brominated, it's adding bromine to the structure, 2 Brs, creating a saturated molecule. And simply hydrogenation, adding the molecular form of hydrogen here to break apart the double bond and going back to the saturated form. So a quick snapshot of how each of those compounds in the double bond breaks, forming a saturated compound. Here is an example of hydrogenation. The last slide showed hydrogenation as this last example down here. Taking a closer look at that, it says most alkene addition reactions are exothermic, heat releasing, creating much more stable compounds as they release heat. As reactants form to products and released heat, exothermic has a more stable configuration. But keep in mind, just because they're exothermic, it gives us no insight into the kinetics of the reaction. Being a spontaneous reaction really gives us no indication of how quickly the reaction is occurring. Just to give an example from everyday life, we could see iron metal rusting. This is a spontaneous reaction, but it takes hundreds of years for us to see evidence of some kind of rusting of your car. I mean, not hundreds, but years and years go by before you can actually see evidence of this. So this is a very long reaction rate. Combustions tend to be very fast reaction rates. Because something is spontaneous, because it's exothermic, gives us no indication upon the rate of the reaction. That indicates the reaction energy. So that input of energy, is the activation energy quite large? It's a very slow reaction. Is the activation energy not so large? It's a very quick reaction. And that's what enzymes do. They lower that energy barrier between reactants and products. If we take an addition of HX, where X can stand for any of the halogens, HCl, HBr, or HI, to give an alkene, creating what's called a haloalkane. Here we have a common name. The IUPAC name would be ethene. Common name here, ethylene. See the double bond? Just to keep of the structure. We have an sp2 hybridization, bond angle of 120. If we react hydrogen chloride, which is an HX, HCl is this example, hydrogen chloride, What we see then is a breaking of this double bond. If we break the double bond, we create sites of attachment. We will create CH3 on one side, and then the chlorine adds to the other carbon. Break the double bond and fill the bonding sites. Chloroethane is the IUPAC name, or ethyl chloride is the common name. This reaction is very regioselective. Think of this root word here as in region, very selective to the region in which this reaction occurs. Regioselective says one direction of bond forming or bond breaking occurs in preference to all other directions. There is a guideline or a rule to help us figure out which carbon is going to accept the chlorine, which carbon is going to accept the hydrogen. And this is a very specific rule to adding an HX. Markovnikov's rule, it's a fun name, Markovnikov's rule. Say it quickly, Markovnikov's rule. Hydrogen adds to the less substituted carbon and X to the more substituted carbon. In the addition of HX to an alkene, hydrogen adds to the carbon of the double bond having the greater number of hydrogens. Add hydrogen to the carbon of the double bond that has more hydrogen. And then, of course, the halogen would add to the carbon that has less hydrogen. This rule is sometimes remembered by saying the rich get richer. In other words, the carbon that has more hydrogen will get even richer in hydrogen. Take a look at this compound, CH3CH. Now I have a double bond, CH2. If I add HCl, what indeed will be the products? Here are the two carbons in the double bond. This carbon has two hydrogens attached to it. This carbon has one hydrogen attached to it. Applying the rule that says the rich get richer, and I break apart the double bond, we go back to start, CH3C. I'm just going to get my sites of attachment here, kind of the original molecule. And now I have to decide where will the H and where will the Cl go. The H and the Cl. The H attaches to the carbon that has more hydrogen. The rich get richer. The hydrogen will attach on the terminal carbon. The chlorine will attach on the center carbon. We've created 2-chloropropane. 2-chloropropane is the IUPAC name. Not CH3CHHCHCl. Not 1-chloropropane. Not that. The rich get richer. Add the hydrogen to the carbon in the double bond that has more hydrogen. Before we talk mechanism, let's add a slide and just consider one more example there. And what I'll do is to pull from 12.6. And this is on page 364. Here's a structure given to us as an example, CH3, C, CH3 heading up. Here's a double bond, CH2, and that's it. And I'm going to add hydrogen iodide. What will the compound result in? What is our product? Well, again, if I consider the structure, we have this methyl group up here. We have a double bond carbon plus HI. Markovnikov's rule states that we add the hydrogen to the carbon in the double bond that has more hydrogen. So let's consider that. Here is the carbon at the terminal end with 2 hydrogens. Here's a carbon with absolutely no hydrogens. If we break this double bond, the hydrogen will attach to the carbon with more hydrogen. So what will the resulting compound look like? Well, here's our CH3, C, the methyl group up high. And this is where we have to decide, where does the H go and where does the I go? What points of attachment? And we know that these are H's over here. Well, the hydrogen attached to the carbon with more hydrogen, placing the iodide on the center. And what have we created? At carbon number 2, we have an iodo group from the term iodine, iodo from this element iodine. And we also have a methyl group at carbon 2. We know that the base word is propane. So in order of priority of the alphabet, we would write this 2-iodo, 2-methyl propane. Shall we try another? Suppose we see a cyclic structure. 1, 2, 3, 4, 5. We'll place a double bond in a cyclopentene. And we'll place a methyl group right here. And we're going to add HCl. What is the resulting compound? Well, keep in mind this attachment here. Kind of consider that we have carbons, just to kind of remind us that there are hydrogens involved here as well. Now I know that this has CH3. Here's the double bond. So this carbon has 1, 2, 3 bonds already attached to it. So it at this point has 1 hydrogen on it. 1, 2, 3 has a hydrogen because it has to have 4 bonds. Excuse me. Linda, I'll start that over. 1, 2, 3, 4. 1, 2, 3, 4 bonds. So this has 0 hydrogens. What about this carbon? This carbon has 1, 2, 3 bonds so far, so it indeed has to have 1 more hydrogen. So it has 1 hydrogen. So when I consider drawing this, I break the double bond, and our resulting compound says, I'm still going to have a cyclopentane, still going to have the methyl group coming off. The hydrogen attaches to the carbon that has more hydrogen on it. So we said that there was already 1 hydrogen, already 1 there because there was only 3 bonds, but the site of the other hydrogen will also be there, and the chloro group is going to attach to the carbon with the least hydrogen. We end up with a cyclopentane. On carbon 1, there's a methyl, and on carbon 1, there's a chloro. Now think about the alphabet when naming that. We get 1 chloro, 1 methyl, cyclopentane. Add the hydrogen to the carbon from the double bond that has more hydrogen. The rich get richer. Let's consider the mechanism. When we talk about a mechanism, we account for the addition of our hydrogen halide to an alkene by a 2-step reaction mechanism. In a reaction mechanism, it is just a step-by-step description of how the chemical reaction occurs. In this particular step-by-step, there'll be two things involved. A step 1, initial, step 2, final change. We tend to see curved arrows to show the repositioning of electron pairs during a chemical reaction. The tail of an arrow shows the origin, and the head of the tail is going to show the new position. So just following the head to the tail says this is the origin and this is now where it landed, and typically we're tracking electrons. A curved arrow showed over a bond is breaking in which new bonds are forming. A reaction mechanism really is a snapshot of how the reaction is occurring. When we added HCl to a molecule of 2-butene, think about that. 2-butene places the carbon in a 4-carbon chain, and we're going to add HCl. Now this is a particular example where the number of hydrogens is equivalent. So either way, we could add chlorine to either carbon and we end up with the same structure. But how does this overall product work? Alrighty. So step 1, the reaction of the carbon-carbon double bond with the proton portion, the hydrogen portion of our molecule occurs first. So the H attacks first. I'm just going to turn that volume down, sorry. When we get a hydrogen added to, we get a secondary, see that 2 primary here degree, a secondary carbocation intermediate. A cation is a positively charged ion, and an intermediate is something that is made as a product in step 1 and immediately used as a reactant in step 2. In step 1 of the addition of HCl to 2-butene, the double bond is broken. Notice this direction of the arrow, and that double bond is going to donate its electron to the hydrogen ion. And if I lose that proton, if I break that bond, it creates a positive site. A carbocation is produced. Again, cations are positive, and it's telling me that it's secondary simply because there's 2 carbons coming off of it. 1, 2, a secondary carbocation intermediate. Well, now that intermediate becomes the reactant in step number 2. So hydrogen is part of step 1, chloride is part of step 2. If hydrogen is positive, we know chloride is negative, and it is definitely attracted to this positive region on this carbocation, and you can see this becomes the site of attachment. The positive charge on this secondary carbocation is literally where we will see the attachment of chlorine. Step 1 says add the hydrogen. We break the bond. Hydrogen attaches to the carbon with more hydrogen on it, leaving the other carbon slightly positive to be a cation. In the second step, the chlorine attaches to that positive region, resulting in our final product, 2-chlorobutane. Step 1, add the hydrogen. Step 2, add the chlorine. Let's add a slide and just take a peek at example 12.7. Here I have a cyclic structure. It's a 6-carbon ring. And the double bond is actually here. CH2 plus HI. We see the product in our example given to us. And right up here, I kind of drew it at a different angle. Let's say it's right here and here. Propose a mechanism for this particular reaction. Propose a mechanism for this reaction. We understand that it is a two-step process. Step 1 is the formation of a carbocation. I'm going to write that. Formation of a secondary carbocation by the addition of the hydrogen. And that hydrogen adds to the carbon that has more hydrogen on it. Markovnikov's rule. So let's consider what we have in terms of hydrogens. And here's a carbon. This carbon has 1, 2, 3, 4 bonds. So in other words, 0 hydrogens are attached to this. Here's the other carbon involved in the double bond, and we can clearly see it has 2 hydrogens attached to it. Step 1 says we need to form the intermediate. So here's my original reactant. Alrighty. And I'm going to say step 1, it reacts with the hydrogen first of hydrogen chloride. We're doing hydrogen iodide. Hydrogen's a +1, iodide's a -1. Where does the transfer occur? Well, we break the bond, break the double bond, and bring that electron over here. Alrighty. So the first transfer is breaking the bond and donating that to the hydrogen. And what results is the carbocation. So let's draw that as the intermediate. Our 6-membered ring. That's a nice ring. And remember, now we have a broken bond. And we've added the hydrogen to the carbon that has the most hydrogen, and the carbocation is right here. Here's the positive charge, and we have our CH3 methyl group. CH2 becomes CH3. Break the bond by donating the electron pair to the hydrogen. That places the hydrogen onto the carbon with more hydrogen. Markovnikov's rule. Now what? We've completed step 1. We have a carbocation intermediate. Step 2 of this mechanism says start with that very intermediate. 1, 2, 3, 4, 5, 6. We have this so far, CH3. And we still have this little positive sign here. Here's the carbocation intermediate, positive charge. And the second step now says let's add the chloride onto that. Always transfer the negatives. It's not chloride, it's iodide. I keep saying chloride. In this example, it wants us to add iodide. Remember, the arrows will transfer from negative to positive, from negative to positive. So now I take the arrow, and remember this iodide has all kinds of dots around it, kind of help us see that this is the site. Follow the electrons. This is now going to attach to the positive side here. And what's the remaining compound? Well, we have our 6-sided ring. We have our methyl group. And from this part, we have our iodide. We added hydrogen to this carbon, the carbon with more hydrogen, and we added our halogen to the carbon with less hydrogen. A 2-step reaction mechanism. Let's consider the addition of water, commonly called hydration. Hydration is catalyzed by an acid, and the most common acid is sulfuric acid. Sulfuric acid comes from the polyatomic ion called sulfate. Hydration follows Markovnikov's rule, where the H adds to the less substituted carbon and OH adds to the more substituted carbon. Add the hydrogen from water. Think of water as HOH. And add the hydrogen to the carbon with more hydrogen. Same set of rules as before. In that first example, we have propene, CH3, CH, double bond, CH, 2. This carbon has 2 hydrogens on it. This carbon has a single hydrogen on it. The hydrogen will add to the carbon with more hydrogen, resulting in, and again, if we just redraw the structure, I have a site of attachment I have to consider here, and I have a new site of attachment I have to consider here, knowing as water is 2 ions, hydrogen hydroxide. Think of those as H plus and OH negative. Hydrogen adds to the carbon with more hydrogen, and the hydroxide adds to the carbon with the less hydrogen. We result with 2-propanol. And again, that's going to be a future chapter, but we see that at the very beginning of our journey that OH is the alcohol functional group in chemistry, and we'll learn that it ends in OL. At carbon number 2, there's an alcohol functional group, 2-propanol. Here we have an example, the carbon-to-carbon bond. Adding water, notice that it's always catalyzed by an acid. HOH, the hydrogen will attach to the carbon with more hydrogen. This carbon will receive the OH. We have 2-methyl, 2-propanol. On the second carbon, there's a methyl functional group and the alcohol functional group, the OH. In this particular reaction mechanism, we see a 3-step process. Adding an HX was a 2-step process. Here we're going to have a 3-step reaction mechanism. Let's take a look. Thinking of water, the step 1, break apart the double bond. Follow the transfer of that electron to the hydrogen ion, forming a carbocation intermediate. Same step, same first step as when we added HX. This carbocation is called an intermediate because it becomes the very reactant step 2 will start with. Alrighty, so here we have the very same structure beginning the next step. In the water molecule, see these electrons around the oxygen here. In the water molecule, follow the electrons. The water is right here on this oxygen, is attracted to the positive carbocation region. The positive charge attracts the negative region of the water. Notice what's happened. The water has literally attached on. Alrighty. So step 2, that carbocation intermediate completes its valence shell by forming that new covalent bond with an unshared pair of electrons on the oxygen atoms, giving what's called see this word, OXONIUM, oxonium ion. That might be a brand new word for us, oxonium ion. We've heard of hydronium, H3O positive, here this oxonium ion. The water molecule is attached to the carbon that had the original positive charge, which was indeed the carbon with the fewer hydrogens on it. Notice this hydrogen here up in step 1, that hydrogen added to the carbon. Now this is not the reaction mechanism. Don't confuse that with following the electron flow. The bond breaks. that's pointing at the positive ion go from the negative region towards the positive region. But this is the site of attachment right here onto this carbon. So over here now, notice we have the CH3. That hydrogen ion came from that first step, leaving this carbon positively charged. It has no electron density left once we broke that bond. The water attaches onto it, creating this intermediate called oxonium ion. This is also an intermediate. The intermediate then becomes the reactant that the next guy will start at. So here's the next reactant. The oxonium becomes a reactant here. This bond, follow the electron density, cleaves this, and you're left with the hydrogen ion that you started with. Remember the definition of a catalyst: something that you start with and end with changes the reaction mechanism, changes the pathway of the reaction, but without itself being used up. The addition of water requires a catalyst to initiate the reaction. The catalyst hydrogen is indeed the hydrogen that gets attached first, and then it's released at the end, giving us 2-propanol. The catalyst initiates the reaction and lets go of the hydrogen to create our molecule of 2-propanol. Important thing here, when we add water, we see 2 intermediates form. The first is a result of the addition of the catalyst, and the second is the addition of the water molecule. We rearrange that hydrogen to place it back as cleave this off. This hydrogen here becomes the hydrogen here. So keep in mind that the same hydrogen that came from the catalyst is not the same hydrogen that lets go at the end, but it indeed recycles a hydrogen and meets the criteria for the definition of a catalyst. When we add bromine or chlorine or iodine, any molecular compound, these are both halogens. Chlorine and bromine react with alkenes pretty much at room temperature by the addition of halogen atoms to the carbon atoms of the double bond. It's generally carried out either by using pure reagents or by mixing them in some sort of inert solvent, such as dichloromethane. This is not a catalyst, it is a solvent in which the reaction will occur in. It's quite common to use this sort of reaction in a qualitative analysis test for the presence of some sort of alkene. If we go about dissolving bromine in a solvent such as carbon tetrachloride, another organic nonpolar solvent quite commonly used in the lab, we'll see that it turns red, and that red is a telltale sign of bromine. In contrast, if we put dibromoalkanes, they end up being colorless. So a single addition gives us a red color, but double bromine gives us colorless. So it's just a nice qualitative test to see what kind of alkene is present. The addition of bromine is, again, just color-based for qualitative analysis, identifying the unknowns. Break the double bond, and each one of the bromines will go on. Let's add a slide here and just take an example. Suppose I have let's just say a I'll draw a 6-membered ring, cyclohexene. Let's add bromine, Br2. If we add bromine, remember we need this to occur in an inorganic solvent. You'll see the solvent written below the arrow. You'll see the catalysts written above the arrow. So let's use an inorganic solvent such as dichloromethane. CH2Cl2, dichloromethane. That would be its Lewis structure there. Alrighty. That looks like an H, but it's a Cl. So here's again the solvent, not a catalyst. Alrighty, nonpolar cyclohexane, nonpolar bromine dissolve quite readily and give kind of the medium for which this reaction to occur. And again, what we'll end up showing is the double bond breaking and a site of attachment to each carbon that was involved in the double bond. So this carbon and this carbon now become the site of attachment for each of these bromines. Remember, bromine itself is a single bond between those two atoms. We've now created a compound called 1,2-dibromo cyclo, I'm going to run out of room, hexane. 1,2-dibromo cyclohexane. Let's try completing this reaction. 1, 2, 3, 4. I'll just keep drawing a double bond, CH3 plus Cl2 in the organic solvent that's nonpolar called dichloroethane. What will the resulting compound look like? Well, the carbons that are involved in the double bond each receive, and this one still has a methyl up here, each receive one of the chlorines. Alrighty. And so what have we created? Well, we have a cyclohexane What about numbering? Okay, well, when we number, carbon 1, 2, 3, 4, 5, 6, carbon 1 gets priority because it can give us the lowest number of both of these branches. So let's just kind of figure out what we have. 1, 2, dichloro, and then we have 1 methyl. Remember, when we alphabetize, the di isn't part of the criteria, but chlorine does come before the methyl group. It's not because of the D in di, but because of the C in chloro. So 1, 2, dichloro, 1 methyl, cyclohexane. Oh, that's not very neat. Cyclohexane. There, I got her. Alrighty. One more, just for the sake of doing one more. How about, let's try CH3, so we'll have a tert carbon here at a terminal N. How about CH, double bond CH2 plus bromine. And again, you'll always see the organic solvent, telltale sign we're brominating. CH2Cl2, I just reversed the order. So here we have a carbon at the end. Let me give it a little more room. I'll draw my product down here. We have a carbon with 3 carbons hanging off of it. So here's CH3, CH3, CH3. So a tert butyl ending here, kind of common. Then we have a carbon that had a hydrogen here, so I'll just point it up because I know one of those will point down now to a chlorine. We have 2 hydrogens and now a second chlorine attaching here and attaching there. Alrighty. 1, 2, 3, 4 carbons is the longest chain, giving precedence to reaching here. So 1, 2, 3 wouldn't matter up, north, or down, so I'll just go straight across. And what would we do to name this? Well, we have a 1, 2 dichloro. And on carbon 3, we have 2 methyl groups. And the whole root word here would be butane. Alrighty. Remember, alphabetizing, C gets priority over the M. Chloro is in the alphabet before methyl. Let's take a peek at the addition of hydrogen, sometimes called hydrogenation, and a reduction in oxidation reduction theory known as redox put it together. It says virtually all alkenes add hydrogen in the presence of a transition metal catalyst, specifically palladium, platinum, or nickel. You're going to see extremely high pressure, room temperature, and a nickel, platinum, or palladium catalyst. Catalysts get placed on the top of the arrow. The conditions in which the reaction is running is placed under the arrow. In a halogenation, add a hydrogen to each of the carbon that contains the double bond. Trans-2-butene becomes a straight chain of butane. Cyclohexene becomes cyclohexane. This addition of hydrogen to an alkene involving the transition metal catalyst. Usually this catalyst is finely powdered, just a very small surface area, and the reaction's carried out by dissolving the alkene in typically an alcohol such as ethanol or another kind of reacting organic solvent. And adding the solid catalyst, we're exposing the mixture to the hydrogen gas at such high pressures. So the addition of hydrogen to an alkene involves this catalyst really by having surface area chemistry occur. The carbon remains absorbed on the metal surface, and the carbon to hydrogen bond forms as the alkene is desorbed. There's a nice picture there on page 370 that's describing how the metal surface is finely powdered nickel, platinum, or palladium actually do surface chemistry in pulling off the hydrogens to create the single bond. And at this point, we will end the lecture on reactions that are common to alkenes, along with their reaction mechanisms. There's a little left of your chapter to look at polymerization, taking a monomer and turning it into a polymer. We highlighted a little bit of that. And you'll do a little bit of reading to finish this off, looking at low-density polyethylenes or high-density polyethylenes, two different classifications of plastics. So as you finish this lesson, you'll do the reading for what are some important polymerization reactions and look at the different structures of polymers as we create plastics.